This week I'll be talking about distribution, and this kind of continues from what we were doing last week. And so last week I introduced a lot of definitions, and now I'm going to go more into the concepts that follow from those definitions. So, but before we do that, just a quick recap on those few ideas. So, can anyone tell me what a variable is?
It's basically a factor in which we are interested. I don't know if the question is how temperature affects the rate of digestion, and so temperature would be the independent variable.
Yeah, so precisely, so the independent variable is an example of it, and then also just generally, but broader than that, would also include just things we're measuring in our study, and it's anything that can kind of identify the individual. And then based on that, we also need to kind of keep in mind the difference between population and sample, because most of the time our questions are about the population, but we can only collect the sample, and we collect data on those particular variables about the sample. Then finally, the next big next two concepts we talked about were parameters and statistics. So parameters are measures about the population once you've kind of collected data on these variables, and then statistic is are the same measures but for samples. And then two measures we talked about were mean and variance. So the mean kind of captures how closely clumped together the values are, so where like the point around which most of the values are, is the mean. More precisely, it's called the central tendency. So when I go into showing the distribution, I think that'll become a bit clearer, because it doesn't necessarily have to be that values are clumped around them. The next concept was variance, which kind of captures how spread the data is. I think before I continue, I want to kind of clarify a term I used last week, which was, I think you had asked a question about mean and average. And so I talked to my friend about like the difference between the two, and essentially in terms of how we use the word, we often just use them interchangeably, and sometimes we'll even call the population mean just the population average.
I think our high school teacher mentioned something like one is that the mean is average without outliers, which are standard depending on what data are included.
Okay, I think whenever I've come across the thing with averages, because you've got different measures of average as well. So I won't be going into all of them here. So you've got the standard arithmetic average, which is the one we normally use to, which is you add everything and divide it. And normally when we say mean, that's what I guess that's what we mean by average, is often kind of the exact measurement technique we use. Whereas, and hence I guess if you remove outliers, then you'd still be calling that an average in a way that's not the mean anymore. But there are different concepts of mean, such as harmonic mean and geometric mean, and that depend on type of the data set, which we won't really cover, and that's not too important. But basically what I wanted to kind of highlight is that they're really the same concept, and when you're using them, we just use them interchangeably. So I'll be talking about the population average or the sample average when I need to distinguish between parameters, and statistics or population mean and sample mean. But more often than not, mean is the word that's used rather than average, because average is usually more specifically for that measure. So by the end of the class, we'll kind of understand when it's possible to make inferences about the population from the sample, and then the contribution units made to statistics as well. So start with, so what is a distribution? So the distribution of data refers simply to the manner in which it's dispersed or clumped together. I showed you guys these two graphs last week. So this was an example of two population distributions. So by central tendency, most of the values are centered around this point. Similarly, for this other distribution, they're centered around that point, and they've got different spreads as well. And similarly, these were samples of 500 observations collected from each of the respective distributions. So the red one was from the red distribution, and the blue one from that one. So the distribution is not actually that complicated an idea. It's just how the data is kind of spread out is what it's capturing. By the way, if you guys have any questions at any stage, just feel free to stop me. So to kind of give you an idea of how maybe the underlying distribution is created, often there's some underlying process that generates a distribution. So this is an example of, imagine if you're a really bad doctor like I am, I'll probably not hit, I'll just randomly be hitting points on the board. And if I was to record the scores that I get, they'll probably be kind of spread out randomly. And often this can be kind of approximated using a uniform distribution, and I'll show that in a bit. But essentially what this is kind of capturing is how the scores were distributed. And similarly, if I'm a very good darts player, most of my scores might be concentrated around one particular point. And I might get bad scores sometimes, but they'll probably be more spread out as well. So the underlying process usually affects the distribution you finally get. So probably the most famous distribution is the bell curve, which is on the next page here. And it was, I think, one of the first discoveries of it was by De Moivre. He was he heavily worked in statistics. So I think he was looking at drawing probabilities of coin flips. So he was looking at, so for example, if you flip a coin 10 times, how many times do you get heads? And he found majority of the times you get 5 heads, but sometimes you get 3, 2, or 1 occasionally. And how often you get them, it started approximating that bell curve shape. And what he found was that as the number of coin flips became bigger and bigger, eventually almost completely, it more strongly kind of followed that shape. An interesting thing about him is that he was slightly insane, and he used to like very religiously note down how many hours he was sleeping every night, and he started noticing a pattern that he was sleeping 15 minutes extra every night, and using that he extrapolated his date of death, and he died exactly on the date that they predicted that he would die. So I've kind of written the equation here, it's not that important. I'll talk about why I really like the equation in a bit, but so this is the normal distribution. It's sometimes referred to as the Gaussian distribution. And this is quite common, and you see it a lot in nature, for example. So often when you're measuring heights of people, or you're looking at the weights or number of fruits the tree produces and things like that, often they'll kind of form this shape in nature. And the reason earlier I talked about the mean and the standard deviation as the only two measures we really need is that this often turns up all the time in nature. And there's another interesting property that I'll talk about in the end, where actually this turns up pretty much everywhere when you have a large enough sample. And the beauty of this is that you only need two parameters to kind of draw this entire shape out. So if you tell me, if I know if a population is normally distributed, and I know its mean and standard deviation, I know everything about the population that I need to know. Because I can draw this entire function just based on those two bits of information. So often in statistics, because this is turning up everywhere, what we're really trying to do is somehow find the population mean and the population standard deviation. Because once we arrive at like those two values, we can get this entire distribution. And then once we get this, then we can start quantifying a lot of things, like how uncertain we are about different concepts. Now, the reason I really like this equation is, so this turns up everywhere in nature. And here you can see two quite common mathematical numbers. So that's pi, and that's 3.14, and it goes on forever. It's an irrational number. And that's another irrational number. That's known as Euler's, I think it's just called Euler's number, but it turns up everywhere. But it's crazy to think that these two completely irrational numbers turn up everywhere in nature, and I think for that I find it like almost quite beautiful, metaphysically speaking. But in maths we normally don't maths normally doesn't give us meaning, but anyway, I like those because of those two things. Actually, I was reading a maths textbook, and often in that it went on in like a paragraph about the meaning of probability, and then it ended it by saying, meaning's great, but as a mathematician it really doesn't matter all that much, it's logically consistent. So interpretation usually in maths is not something we can
Sorry, just a quick question.
Yeah.
So any sort of bell curve normal distribution, is that just any distribution that has a central tendency, or are there other distributions with a central tendency that wouldn't fit that?
So actually,
equation.
So this precise equation is the normal distribution. But you get distributions that look very similar to this, but are slightly different.
Okay.
So actually on the next page you'll see this T distribution. This looks very similar, but this is not the normal distribution. And the reason is that we have a lot more things clumped near the center, and a lot more clumped right at the tails, but very few around these parts. And they might look only slightly different, but actually a lot of the problems in the financial crisis happened because they assumed stuff behaved the other way, but it actually behaved like this. And they're significantly underestimated risk because of that. Yeah, so you do get the bell curve shape in other places. So these are just, so the normal distribution is not the only distribution, there are many others. So this is a uniform distribution here, everywhere the probability is essentially the same. And as I mentioned, the t-distribution. And you get various things distributed in these ways. So you've got height, weights, measurement errors, test scores, intelligence, but IQ is distributed normally. Actually, IQ is a bit of an unfair one to put here because by design it's constructed so that it is distributed normally rather than it being an actual phenomenon that ends up like that. And then you've got uniform distribution. So often on a computer when you have a random number generator or on a calculator, it's a uniform distribution. I don't want to use random number generators because they aren't actually random, they're quasi-random structures, but yeah. But in terms of predictability, the behavior is still random. And then you've got the student's t-distribution, which I showed in the previous one. So financial returns tend to be distributed t-distribution. So most days you won't get much change in the stock price, but days that you do get a change, it really changes a lot. And so that's modeled well by a t-distribution. And then actually, so I'll get onto Guinness in a bit. So an interesting story is that there was this, in the financial crisis, what happened was they can calculate the probability of an event happening. And so when the financial crisis happened, the probability of that happening was 1 times 10 to the minus 60 or something. So that might be meaningless, but what that means is that it happens once in every 10 to the 60 days. To give you an idea, the universe only exists for 10 to the 12 days. This is the magnitude of number of days by a factor of like 50 higher. And the reason was that a normal distribution gave them that answer, but a t-distribution would have more realistically told them that actually it's not. It can happen. So the t-distribution was actually, so you might have noticed that it's called the student t-distribution. I've not put an apostrophe, that's actually student's t-distribution. So it's quite interesting because there was never anyone called students, but the reason it's called that was it was discovered by this man, William Seeley Gossett. He was a scientist at Guinness, and what he was working was on barley, and I think he was looking at the best yielding barley, but I don't know the exact dynamics of the experiment he was conducting. But more interestingly, what he noticed was that when he plotted it, it wasn't exactly normal, and it rather formed this t-distribution. So he was a mathematician from Oxford, and he was quite good friends with his, I think he was a professor there, Pearson. So if you've done biology, you might have come across the Pearson Rank School. But if not, Pearson's quite a big statistician. So he worked with him and kind of derived the t-distribution. But Guinness had this rule that if you're an employee at Guinness, you can't publish your results in a journal. So they agreed to allow him to publish his results under a pseudonym of student. At that time, Pearson didn't take credit for it either because he thought the student t-distribution is a pretty useless thing, will never really be helpful. So he published it under the name students, and today in every textbook you'll have kind of these statistical tables at the end next to the normal distribution with the student t's distribution. Just in terms of use of students t, you use it when you've got very small samples. When you have very small samples, things seem to be distributed in a student t rather than a normal. So, and actually when you get very large samples, most student t distributions become normal distributions. But that's not that important. It's just some interesting information to so does anyone have any questions at this stage? Okay, so now we've got the few concepts with us, which is kind of what a sample is, what a population is, a few measures, mean, and variance, the difference between parameters and statistics, and also now kind of the idea for distribution, how the data is spread. So the question is, how do we get from a sample to population? Because ultimately that's what we're interested in. And under what conditions can our measures of from a sample be used to make inferences about the population? So when can we use statistics to make conclusions about parameters? And yeah, so just a quick recap, as I was mentioning earlier, a sample mean or sample average is something that we use to measure information about the sample. And I think, and the reason it's important is that in terms of the population, as I mentioned last week, is that often our hypotheses are about the average effect of things at the population level. So it's what is the average effect of student grades of classes becoming smaller, for example. And hence, we're usually interested in the mean. And a lot of policy is driven based on the mean. So if, for example, before the government introduces changes to benefits policies, and if you read the labor economic papers, they'll have a lot of things on the average effect of various government policies, and based on that, they end up deciding whether to go through. Okay, so one thing we need is that our samples need to be randomly collected. Otherwise, they won't be representative of the population. And I think it's quite an intuitive idea in the sense that I think the example I used last week was that if you're interested in the on the average number of people who are churchgoers, and you only collect data of people who go to church, then you will not get a good conclusion out of that because it isn't representative of the population. And so the idea is if you just randomly pick maybe 10,000 people, they're likely to be more representative, and hence we need random sampling. So otherwise, non-random samples are kind of subject to bias. Okay, so now that we have a sample that we've collected randomly, we need to look at conditions where we can use the sample now to make conclusions. So for this, I'm going to talk about the law of large numbers. Now the law of large numbers, what it basically says is the average of the results obtained from a large number of trials approximates the true population value. I'll try to give an intuitive example of this. But yes, it basically means as your sample gets bigger and bigger, the average equals the population mean. And for example, if you think of LSE heights, if you collect 2 people and you calculate their average, it's probably not that representative of the actual average height of LSE. But if you collect maybe 1,000 people, the average you calculate is more likely reflective of the average height of LSE. And it's basically that idea. But to be clear, this is about the statistic equaling the parameter, rather than the distribution equaling the sample distribution equaling the population distribution. So to give you an idea, so suppose you play a game, you flip a coin, and if it's heads, you get $1, and if it's tails, you give the casino $1. Right? So what would you expect your payoff to be on average?
0.
Yeah, so exactly 0, right? Now, the thing is, you can't actually ever get 0 in any given game, but that's the average. And what I'll try to show is that on average, the average actually tends towards 0 as you reach infinity. So this is kind of a plot of the total payoff. So this is not average payoff. And this is maybe what your bank account might look like on that day. So this is 100 trials. So initially you're winning a bit, then you lose, and then you win occasionally, you lose, and so on, it fluctuates. But here's what the average would look like. So maybe the first game you won, so you got, and you calculate the average with one game, so you'll get a probability of 1. And then maybe you lose the second game. So then the second point, the average would equal a half. And so you keep repeating this process, so every time you play a game, you look at the total bank account, the amount of money in your bank account, and you divide it by the number of times you played it. And eventually what happens is that it basically tends to 0. So if you see maybe at the 50th trial it's not at 0, it's at 0.21. And you might believe that actually in this coin flipping game you're beating the casino in the long run, but eventually probability catches up with you, and at 1,000 you reach 0 at 800. So what the law of large numbers says, it doesn't say anything about small samples. And it's really about as you approach infinity. Often this would be the notation, and so if it's I don't know, my name Manav, and then T would be 2008, so that would be my income in 2008 is what that would capture. So in this, the sample size is usually the number of eyes you have, so the number of unique people you have rather than the unique observations. So right now in my dissertation I'm looking at banks, and I have around 16,000 banks. So that's my sample size is 16,000, but I have my total observations around 2 million observations. So 2 million, actually I'm just thinking, would I say I have 2 million sample size? No, I would say I have like a sample of 16,000 banks, but my observation is 2 million. Yeah, but that's the difference. But yeah, usually in most cases that you'll come across, it's not a panel, and it's just you observe them in a cross section, so in one time period, and then it's just the number of people you have.
Yeah, I think that's why I got confused, because I think panels.
Yeah, so so it's actually some of the concepts I'm talking about here don't necessarily that easily apply to panels, because here there's an implicit assumption I was talking about earlier about independence. So each, for example, each coin flip was independent of the previous coin flip, like it doesn't affect the next one. That's not necessarily true in a panel, because your income the year before probably affects your income next year. So the maths changes slightly, but most of the intuitive ideas are essentially the same. Yeah, so does anyone have any other questions? Right, so now we've kind of estimated the sample mean, and we want to somehow capture the uncertainty around our estimate of the sample mean. So how close are we to the population mean that we really want to estimate? Now, so if we can somehow kind of find a distribution of the sample mean, that will allow us to indicate an idea of like, actually I'll get to that later. So to kind of explore that idea further, we want to look at something called the sample mean distribution. Because once we have that, then we can maybe see how our measurement of the sample mean varies over time, right? So if we had some other sample, what would our average be? And so is there a way to capture a sample mean distribution? Now this might not maybe make sense, because when we have a sample and we calculate the sample mean, we only have one number, right? Like if you recalculate the sample mean of that of a data, we'll get the same number again. So it's not really varying. So how do we kind of generate this distribution? And it's this kind of theoretical, hypothetical idea we come up with known as repeated sampling. So we asked this question: what if we did this experiment but recollected 10,000 more random observations, and then we repeated it and collected 10,000 more observations? So every time we collect 10,000, so if let's take that as the example. So now let's say you have 10,000 people, and you take 20 random people. You kind of calculate the mean you get. Let's say you're interested in heights, you calculate the average height those 20 people have. And you put those 20 people back in the population, collect 20 more people, and you calculate the heights. And the thing is, that's the concept of, so that's the concept of repeated sampling. It's more of a theoretical concept because you're not going to actually do that. But this approach of thinking helps us develop something called the sample mean distribution, which we can then use to capture uncertainty about the process of going from sample mean to population. Yeah, so I've done this, here I've tried to demonstrate that. So imagine this is the actual underlying population of LSE heights, right? And what I do is that I collect, actually it's not heights, but so basically here the population mean is 0. This is called usually standard normal, so it's got a variance of 1 and mean of 0. But what's more important focus is on the mean. So there's a mean of 0, and here I've collected 75 random observations from this, so a sample of 75. I've calculated the mean here. I've put the 75 back, calculated another mean, and calculated another mean. So what you'll notice is that all these sample means are quite close to the true population mean of 0. But they're not exactly that, and more importantly, every time I get a different value. So the thing is, the sample mean is varying dependent on the sample I'm collecting. And hence, maybe we can use this idea to then maybe draw a distribution of the sample means themselves. Yeah, so just as I was saying, there seems to be uncertainty about our estimates and the quality of our estimates. So we're going to try to use this variation to then construct a distribution and then use it to quantify our uncertainty. So this is probably the most important theorem in statistics. It's called the central limit theorem. So in statistics, I would say 90% of the work you do is essentially law of large numbers and central limit theorem, and everything really follows from these two results. There's this other field called non-parametric statistics that does other stuff, but you don't deal with them. It's terrible and difficult. So I'm going to try to. This was developed by Pierre, Simon, Laplace, and they're actually a huge family of central limit theorems, but they all basically derive at this, try to reach the same result. Okay, so we've already established that the sample distribution approximates the true population distribution better as the sample size gets bigger and bigger. And we've also seen the sample mean approximates the population mean larger the sample, and it actually approximates it better, right? Like intuitively that follows from the law of large numbers. So if you have 100 observations, the sample mean might vary a bit more from the true population mean, whereas if you've got 1,000,000 observations, it's probably likely to be a lot closer to the true value. Now what the central limit theorem, like the conclusion it reaches, is a very powerful one, which is that no matter what the true underlying distribution of the population is, the sample mean distribution will always be a normal distribution given your sample size is big enough. And so I think it's easier to draw to kind of explain what I mean. So imagine that the underlying mathematical process, the distribution, I'm trying to think of some random, so this would be frequency here usually. And here would be, let's say, car size. Right? What this means is even if you have a crazy distribution here, right, there's no way for us to mathematically figure out what this is. Or there might be a way, but it's not worth the effort to go through to kind of figure it out. So what this means is, let's say I collect a sample of some size out of this. Let's say the sample size is 1,000, right? So sample size equal to 1,000. And then I kind of take those numbers, take those thousands, and then 1,000 observations, and I calculate an average for them. And then I put those 1,000 back and I repeat the process. So this comes to a repeated sampling. And if I plot those sample means, so if you remember last week I showed you the notation of for average, so that's a class size I. So that's the notation for the bar on top for average. And if I plotted that, what central limit theorem says is that it will look like this, regardless of what this looks like. Right? Do you have any questions?
Yeah, could you just, I don't know, I don't actually fully understand this part. I don't understand why that would turn, I don't know, could you just elaborate a little bit?
Okay, sure. So, firstly, does everyone understand the concept of sample mean? Because I think that is quite important. I feel a lot of statistics students in general don't really understand this concept. So this is not the distribution of the actual observations. This is the distribution of the measure of the, so we're taking them and calculating a particular number of mean, and we're plotting it here. So imagine this is not the, imagine like we did for 10,000 values. I think I have a graph on the next page which demonstrates this better. Okay. Right, okay, so I'm going to try to capture this idea here. So let's say you have this as your underlying distribution of the population. So this means that you have so many cars, whatever that car size might be, maybe let's say some arbitrary number, 100 as a car size unit, and you've got that many cars, and that's the probability of that, and you've got that many cars of that size. So now let's say you collect 10,000, you collect a sample of 1,000 randomly from here. So you might collect some values here. You're more likely to collect values here because most of the values, there are a lot more cars here of that size. You'll collect some values from here, some from here, and some from here. And then you'll take those 1,000 numbers and you'll calculate an average for them. Right? And you'll plot its average. So that average would be single point numbers. Right? Then you'll put those 1,000 back in, and you'll take another 1,000 random points from here. And then you'll take them, you'll calculate another number, and you'll like whatever number you get, you'll plot it here, or whatever it might be. And the kind of unintuitive outcome that the central limit theorem comes out with is that when you're done with this process, repeating it like an infinite number of times, and you can join all those dots, make this shape here, the normal distribution. Again. I think it takes quite long to get your head around this, but I don't know if this helped.
So in this case, is the population mean 0? Or is it not traceable because
you could trace it, but I'd imagine it's basically where the majority of the. I would imagine it's somewhere like here.
Okay.
But it would, yeah, you'd have to take each point and kind of figure it out.
Right.
And so if this is the population mean mu here, the thing is this would be centered around mu.
Oh, okay.
Right. Sorry,
Yeah,
I didn't find that out. And but if your underlying population is something completely different, so. So obviously, if you have a normal distribution, this would automatically follow. And actually, your sample doesn't even need to be big for this to follow in that case. But yeah, but if it's something crazy, something that looks like this, right?
Mm.
Even then, it'll follow this shape because the mean of this is probably somewhere around here.
Yeah.
Too.
Okay.
And that would be mu, and it would turn up.
Okay. Yeah, I've got it.
Okay, so this is the central limit theorem, and what I've done here is I think the underlying distribution of program was a normal distribution, and I asked the computer to take 100,000 observations from the distribution, take 75 observations from the distribution, and repeat that process 100,000 times and plot it. So it took those size of 75, calculated the average, and that did that 100,000 times and plotted it, and this is the shape you get. And this is what I kind of wanted to highlight, that it becomes a normal distribution. Now the reason this is so powerful is that essentially in statistics we know everything about the normal distribution. There's probably very little left to research about the normal distribution, right? And because we find out that a sample mean is distributed like this, we can use all those thousands and millions of theorems we have on the normal distribution. And more often than not, we don't really care about the underlying population distribution, right? Like, all our hypotheses are mostly about the average effect. The thing is, now we know how our sample averages are distributed. So now we can use this to then capture the uncertainty about our estimates about the population. Yeah, so using the sample mean and the sample variance, we can calculate this entire shape. And as I mentioned earlier, we only need 2 measures to find out the shape of the normal distribution. If you have the mean and the variance, we know everything about the distribution. So the law of large numbers gives us the result that the sample mean reaches tends to the population mean. An extension of that basic idea also gives us tells us that the sample standard deviation tends towards the population standard deviation as the sample gets bigger and bigger, which both follow from the law of large numbers. And then the central limit theorem tells us that it's distributed normally, right? So now we know the variance and we know the mean, and we know that it's normal. So using these 3 pieces of information, we can kind of find out everything about how the mean we're estimating is distributed. Okay, so I think this is the last slide. Okay. What I'm showing here is a combination both of the central limit theorem and the law of large numbers in action. So I'll describe what's going on here. This is basically a count. That's not too important. Right? Think of this as a frequency if I just rescaled it to 0 and 1. But and here I've plotted the sample mean. So these are sample mean distributions. So when you have a very small sample size, let's say 10, and let's go back to the LSE heights example. We're interested in the heights of LSE students, and we collect a sample of 10 people, and we estimate the average. The thing is, because it's such a tiny number, a sample, there's a chance that it might be very unrepresentative of the population. And so estimates of the average might vary considerably. And this is what the red line is capturing. So the red line captures the distribution of a sample size of 10. So as you can see, yes, more likely than not, it will be bang on. So 0 here, sorry, 0 is the population. So more likely than not, we'll capture the population, but it varies considerably. But as the samples get bigger and bigger, the sample mean distribution variance decreases as well. So let's say we collected 100 people, data on 100 people's heights instead, and calculated the sample mean. Again, you will get variance because those observations of 100 between samples might not be identical. But our estimate is likely to vary a lot less. And so similarly, just continuing with that same argument, if you get more and more, the variance decreases, and eventually as you tend towards infinity, it becomes 0 by the law of large numbers, and our sample is mean is equal to the population. And hence these are quite powerful results. So now we can use sampling as a process to make conclusions about our population and use it to answer questions that we're really interested in. So these are actually the ideas that I wanted to cover today. So next week I'm going to basically take this idea and extend it a bit to, so once we have a distribution, we can now start quantifying the uncertainty more precisely. And the way we quantify that uncertainty and test estimation-based hypotheses are something called hypothesis testing, which I'll talk about. And kind of, I want to highlight maybe how in academia sometimes papers are just published because they kind of meet something called a significance level, which will make sense next week. But actually, there's a lot of different types of uncertainty, and hypothesis testing only captures one of them, and hence it's not really a complete tool in itself. And I also want to talk about causality more precisely. So maybe our hypothesis tests are great, and like our mean looks great, but maybe we aren't capturing causality, and we're missing something else. So I'll try to define causality more formally. And once we've done that, we'll, I think, have the key framework we need to exploit the tools that we often use in statistical research, such as RCTs, regressions,